who discovered dinosaurs in the first place? We know the ancient Romans and ancient Greeks and Chinese, they actually uncovered dinosaur bones from the ground, but they didn't know what they were. In fact, they attributed these dinosaur bones to dragons at the time. Then it wasn't until about 1677 when the first documented dinosaur bone was discovered, but they still, at that time, didn't really know what dinosaurs were. They attributed those bones to giants, because biblical creationism was the dominant theory at the time. So people thought that these were from the giants that God created. But few people know the legendary story of Mary Anning, the mother of paleontology, the one who changed everything. Mary Anning was born in 1799 and she grew up poor in a neighborhood on the southern coast of England called Lyme Regis. Her father was a carpenter, but on the side for extra money, he would sell seashells and fossils from a nearby beach. This beach was known for the amazing fossils it had. People would find fossilized ammonites and belemnites and crocodiles and marine reptiles and fish, and wealthy people would flock to the area to purchase these fossils as souvenirs. And so Mary, as a child, would help her father hunt for these fossils on the beach, especially during rainy days because the rain would wash away at the cliffs there, and so it would reveal all those fossils. Mary's father taught her everything she knew about how to find fossils. I mean, Mary was not very educated at all. She had basic understanding of reading and writing because they were poor, they couldn't really afford school. But one day, when they were fossil hunting, Mary's father slipped and fell off one of those cliffs, and he sustained major injuries that unfortunately, after a few years, he would pass away from. Mary's father left behind tons of debt. But fortunately, Mary and her brother Joseph would go out back to the cliffs and continue hunting for fossils to support the family. And this is when they began making major discoveries. One day in 1811, just 1 year after their father's death, Joseph found a fossilized skull in the cliffs. And Mary came along and eventually uncovered the rest of the skeleton, and they found it was an ichthyosaur. This was an extinct marine reptile. Now, at the time, they didn't really know what it was, but after months of digging and carefully excavating it, they found it to be a 15-foot complete skeleton of an ichthyosaur. This was the most complete example of an ichthyosaur ever found. The skeleton was sold to the Royal Society of London, but over time, as Joseph grew up, he found a job to support the family, and Mary was left being the sole fossil hunter, who went on to find more of these ichthyosaur fossils, and this gained the attraction of scientists and geologists in the area. Then in 1823, Mary Anning discovered a plesiosaurus skeleton, a nearly complete one, and this shocked the scientific community. In fact, many scientists didn't even believe it was real until they further investigated it. Now, Mary Anning was very meticulous. Every time she excavated fossils, she would write down and diagram the entire complete skeleton. And so lots of scientists used her work in their publications. However, Mary Anning was often never given credit because she was a woman, and at the time, women were not able to be part of the Geological Society. But that didn't stop her from continuing her discoveries. In fact, she was the first one to interpret coprolites, or fossilized poop. She would look at these samples and crack open this fossilized feces and discover bones of fish. And so she was the first one to discover what these ancient marine reptiles would consume and where they fit in their niche. Then in 1828, she discovered the second ever pterosaur fossil, which was nearly complete, enabling them to confirm that they could indeed fly. So over time, Mary Anning would develop friendships with many geologists and scientists in the area, and she would help them discover things and help them in their work, even though she was still never given credit for this. She also helped challenge the dominant theory at the time, which is creationism. A lot of scientists didn't believe that the Earth was old. They believed that the Earth was 6,000 years old, and extinctions were not understood. They didn't think that species could go extinct because they thought God would never make a mistake. But Mary Anning understood the different layers, and she discovered that there was a timeline between these layers. And so the principles that Mary Anning used, even though she had no education in this, we still use today in modern paleontology to discover dinosaurs. Her meticulousness, her preciseness, these are all principles we use today in modern paleontology because of her. And so that's why she's called the mother of paleontology. Now, unfortunately, Mary Anning's discoveries over time ran out, as there was less and less fossils to discover on the beaches of Lyme Regis. And so even up to the day she died in 1847, she was never really recognized for her work, and she never really attained wealth from her discoveries. It was only decades later after she died that she was recognized for her contributions to paleontology. And it was only a couple decades after she died that people really began to understand dinosaurs as a separate category of extinct animals. But none of that would have ever happened without her work. And so that's the legend of Mary Anning, and the beginning of our dinosaur series. So stay tuned for the next ones. People used to think that dinosaurs were just oversized lizards. In fact, that's where the word dinosaur comes from. It means monstrous lizard. So in the 1850s, when people just were beginning to discover dinosaurs, they would reconstruct them as walking on all fours, and their tails dragging behind them on the ground. When people first examined these dinosaur skeletons, it reminded them a lot of iguana skeletons. In fact, they called some of the first dinosaurs they found iguanodons. This is a dinosaur park from the 1850s with some of the first reconstructions of dinosaurs ever. And if you notice, they got almost everything wrong. From the iguanodons looking like iguanas, which now we know that's false. They walked upright and their tails were not dragging on the ground. They didn't walk on all fours. Not all the time. They even confused the iguanodon's thumb spike for a nose spike like iguanas have today. But now we know that that was actually a real thumb spike they had. And look at how wrong they got their ichthyosaurs. They didn't flop around like seals. They were fully marine reptiles. Other depictions of sauropods from this time showed that they thought they were swimmers, that they swam in the waters, because they believed that they'd be too big and heavy to walk on land. Well, now we know that's false. Now we know they could not have been swimmers, because if they were in the waters, all that water pressure would make it impossible for them to breathe. And then going into the early 1900s, as more theropods like T-Rexes were discovered more and more, people began depicting these animals as if they were walking upright, but their tails were dragging on the ground like Barney. They were again referring to lizards as their tails dragging on the ground as evidence that all dinosaurs did that, but that's not true. Now we know that dinosaur tails were very strong and stiff, and their tendons and meat held them together. They were very heavy and very strong. It helped them counterbalance their weight as they ran, as they hunted. It would be a terrible drag on their body to walk upright and have their tails dragging on the ground like Barney. That would make no sense. In fact, this is where Godzilla from the 1950s got it inspired. If you notice, Godzilla is an upright dinosaur kind of looking thing with a long dragging tail behind it. The general idea was that these dinosaurs, they went extinct because they were just too big and sluggish and too dumb to compete. But now we know that since the 1970s, a lot of these dinosaurs had feathers and they were very active. Around the 1990s is when the paradigm shifted from these dinosaurs as just like these sluggish lizards to actually they were kind of like birds. They were very bird-like. As scientists around the world began to discover feather impressions and skin tissue impressions in fossils around these dinosaurs, they began to say, yeah, these dinosaurs were likely feathered and very active. But ever since Jurassic Park came out in the early 90s, a lot of paleo artists in their reconstructions of dinosaurs were a bit too conservative in giving them meat and flesh around their bones. This is called the shrink wrapping effect, and this has been plaguing the paleontology space for a couple decades now. A lot of paleo artists are just scared to add fat deposits and more skin and lips and things like that to dinosaurs, because they want to be scientifically conservative. They don't want to do too much. And so if you notice in the last 30 years of Hollywood movies, dinosaurs are typically depicted as very lean and very bony, very scary. People want to go see those movies. They don't want to see a movie where dinosaurs look like big overweight chickens. But this is very important to get accurate reconstructions, because if we don't do it, take a look at recent comparisons to modern day animals like zebras, for example. This is a shrink-wrapped zebra. If paleo artists of today were to reconstruct a zebra as they do dinosaurs, it would look like this. They're just too conservative on the meat, and they gotta add more to accurately depict modern day zebras. And this is what swans would be like, and baboons, and hippos. And this guy looks crazy. It's an elephant. See, we forget that these big bones require strong muscles and lots of flesh to accompany it, so they can move these big bones around. So our depictions of the T-Rex have evolved in the last 30 years. Back then a bit more leaner and skinnier, but today it's a bit chubbier. And it kind of looks like a chicken, oversized chicken. And so now, today in 2025, we know that dinosaurs were way fatter, way chubbier. They had lots more flaps of skin on them and feathers and fur all around their bodies than we typically would depict them to have. And today we also vastly underestimate how complicated the dinosaurs were. They weren't just these big old dumb things. They were very complicated. They had social interactions. They were mating in certain unique ways as modern birds do. And this is the true heart of science and discovery. That when our intuitions about the world are wrong, when we're proven incorrect, every mistake opens a new door to a reality we could have never imagined before. In 2005, scientists recovered soft tissue from a T-Rex fossil dated 68 million years ago. But what does that really mean, and how is that even possible? Fossilization mainly happens when an animal dies and is quickly buried by sediment. For example, a mudslide or a volcano erupts and they're quickly covered and buried. The soft tissue decomposes, but the bones remain under all that sediment, and water from underground can slowly seep into the bones and the porous spots and cavities of the bones, and this mineralizes them and it petrifies them essentially, and the bone quickly turns into stone. However, there are some very rare cases where even the soft tissue can be preserved. When Mary Schweitzer discovered this T-Rex femur bone, she had sliced it in half, exposing the middle cavities. And when she dissolved the mineralized bone in a weak acid, she saw structures that resembled blood vessels and red blood cells and flexible tissue. After a couple years of research, the team found out that hemoglobin inside of the dinosaur bone, in the middle cavity of it, which was surrounded by tons of dense bone, that hemoglobin released iron, free, very reactive iron. The iron catalyzed the formation of free radicals inside of the bone, which are molecules that attach to proteins inside of collagen. So if you think of proteins and collagen, think of them like strings, stringy material that bacteria and other things and other chemicals can destroy. However, the free radicals in this case would react with the proteins and tie them together in something called cross-linking. So the proteins were tethered together and they became stronger, more durable, more longer lasting. Way harder for bacteria and other chemicals to break them down. And they performed an experiment that confirms this. They took a blood vessel from a living animal and they introduced iron-rich hemoglobin to it, and they found that that blood vessel didn't decompose as fast. It lasted hundreds of times longer than typical. Now, it's important to understand that the soft tissue from these dinosaurs aren't like living, fresh tissue, right? This is highly mineralized material. And the blood cells that we're talking about were actually just iron-rich structures that resembled blood cells. So after 68 million years, we're left with the very last remnants, the very last, very small structures of collagen and skin. And the reason why this T-Rex in particular was so well preserved is because they found the fossil near a river in Montana. And so the dinosaur was likely drinking water or something, and it somehow fell into the river, got swept away, and over time sediments and mud and dirt buried it very quickly. So it left no time for bacteria to get to it or other scavengers to get to it. And it happens to be this location of the dinosaur that was found was very stable over the last 68 million years. There wasn't too many chances for this fossil to remineralize a certain way and for other chemical processes to occur and destroy all the tissue. So there has to be a very perfect storm of events to happen in order for soft tissue and all these things to be preserved the way they are. And so after this 2005 experiment, scientists have found even more examples of cartilage and proteins and pigmentation traces inside of dinosaur fossils in the last 20 years. And now your next question is probably going to be, well, how about DNA? Well, DNA is a different story because it has a half-life of 500 years approximately, and that means that after 500 years, half of the DNA structure is remaining. And so after another 500 years after that, another half is gone. And so the oldest sample of DNA that we can retain in any degree is about 1 million years old. When an animal dies, certain enzymes are released in the cells that break down DNA. It kind of self-destructs. And in case of the hemoglobin, preserving the blood vessels, well, unfortunately, the free radicals enhance the destruction of DNA. They don't preserve DNA. Although we might find DNA remnants in dinosaurs, the basic structures that are really broken down, we'll probably never find a kind of way we can intelligibly sequence DNA from dinosaurs based on fossil samples. So no Jurassic Park anytime soon, thankfully. See you next time on the next Dinosaur series video. Dinosaurs didn't breathe the way we do, and that's the secret behind why they got so big. See, a lot of people think that it's the high oxygen levels back then that made them so big, but actually that's not true. In fact, during the Triassic and Jurassic periods, oxygen levels in the atmosphere were 25% lower than they are today. It was actually the adaptations of their respiratory systems during the low oxygen periods that made them eventually be so large. Dinosaurs had very different bones than we do. Their bones are more hollow, and they had a honeycomb structure inside of them that would connect them together, making them strong but lighter. See, our bones are more dense, but they're heavier, and so there's a trade-off. If you know engineering, you actually want a hollow structure connected with struts inside that's actually more stronger than even a solid rod per weight. Dinosaur bones could be way bigger and yet lighter than ours and retain the same strength. So over the past few decades, scientists have noticed that dinosaur bones are very similar to bird bones, modern day birds. And we know that modern day birds have air sacs throughout their bodies, not just lungs. Those air sacs fit around and inside of their bone structures. And dinosaur bones have those same cavities that allow for air sacs. When a bird breathes in, that air goes past their lungs into rear air sacs, where that air is stored. And then when they exhale, that air from the air sac is pumped into the lungs. And then when they inhale again, more air goes into the rear air sacs, and the air from the lungs goes into front air sacs. And then when they exhale again, air from the rear air sacs goes back into the lungs. And so they always have fresh air going into the lungs even when they're exhaling. In other words, air is moving always in one way. It's unidirectional. See, in our lungs, we have to breathe in and out from the same place, right? But in their lungs, it's just a one-way circuit, like a racetrack. And so this allows birds to fly very high up where there's low oxygen levels, and allows them to never almost run out of breath. They can fly for days without running out of breath. And more importantly, this keeps oxygen concentrations in their lungs high and steady at all times. See, in our lungs, we breathe in and breathe out, but that air is being mixed with CO2, and so oxygen concentrations are lower in our lungs because we use the same lungs to breathe in and out from. And so dinosaurs like the T-Rex and sauropods especially, they likely had these kinds of air sacs throughout their entire bodies. Now, dinosaurs probably had a more primitive respiratory system than modern day birds, but we know that dinosaurs must have been way more efficient at getting oxygen throughout their bodies to maintain their body mass and also stay cool. And so equipped with this better, more efficient respiratory system, dinosaurs, especially going into the Cretaceous period where oxygen levels were higher than today, they were really able to get oxygen into their bodies and support those huge body masses. However, this all began about 230 million years ago when dinosaurs were just beginning to emerge and had to adapt to the low oxygen environments. This evolutionary pressure they were forced to undergo enabled them to later on become larger and more dominant. And it's also what laid the foundations for modern day birds to rule the skies. Okay, we are vastly underestimating how socially complex dinosaurs were. Last year, paleontologists uncovered a huge dinosaur footprint track. This means that dinosaurs traveled and migrated in herds together. But this track found that there were several different footprints of different species of dinosaurs. They saw side by side 5 ceratopsian footprints and 1 ankylosaur footprint, meaning they were all moving in the same direction. And perpendicular to them, they saw a T-Rex footprint. This means that dinosaurs between species would form an alliance, protecting themselves against predators. But that's just the beginning. Another study looking at bone beds of a particular duck-billed dinosaur found that juvenile dinosaurs were grouped together. They were separate from the adults and the grandparent dinosaurs. In these juvenile groups, dinosaurs would play around with each other, they'd play fight, they would develop their survival skills with parents watching from afar. What this means is that just like in some mammals of today, the children would all group together, play around in little nurseries. And the dinosaurs would stay in their nurseries until about 4 years old when they reach breeding age, and so then they would get mixed back into the multi-generational groups of their adults and grandparents. Sauropods took it to another level. Last year, another major discovery with 200 sauropod footprints were discovered, meaning that they also traveled in herds together. But the female sauropods specifically would all gather together in little colonies where they would all lay their eggs at roughly the same time. In fact, paleontologists looked at the different layers of that area where they would lay their eggs, and they found in different layers, in other words, over thousands of years, they saw eggs, which means that these dinosaurs would come back to that same spot for thousands of years and lay their eggs and raise their children like a daycare. And then just a few weeks ago in Colorado, scientists uncovered a huge mating dancing arena for theropods. They saw over 25 little spots where theropods would scrape the ground. It was the site of an ancient lek, or a communal mating ritual, where male theropods would go there and perform dances in front of females for courtship. Males would try to scrape the ground and pretend like they're building a nest to impress the females. And this is very similar to what birds of today do, like the greater sage grouse. The male dinosaurs likely did some bobbing and bowing and flapping of their wings to impress the females. So just imagine a group of 15 or 20 different theropod dinosaurs dancing in front of female dinosaurs. Now, this is more speculative, but it's possible that hadrosaurs use the constellations, the stars, to navigate when they're migrating. We know that modern-day birds have sensory systems that allow them to orient themselves with the stars when they're migrating. And so it's possible that ancient dinosaurs also had very similar, perhaps more primitive sensory systems that allow them to use other natural cues when they're migrating, like perhaps the stars. And so how we know all this is by inferring it based on modern-day bird behaviors, because we know that birds today are dinosaurs. And so the ancient dinosaurs or their ancestors. And so the evidence is growing that dinosaurs of the past are far more socially complicated than we give them credit for. People forget that the dinosaurs dominated for a good 130 million years, and there was thousands of different species of dinosaurs. It wasn't just like, the T-Rex and a couple others. There were thousands, each in their own individual niches, on all continents around the world, even snowy polar regions. However, it's important to know that it wasn't just all skill with the dinosaurs, it was also some luck in there. Before the dinosaurs emerged, their ancestors were saved by the Permian extinction, which wiped out almost all the competition for them, and so that allowed the archosaurs to eventually evolve into dinosaurs and thrive. So the first dinosaurs appeared about 230 million years ago, things like the eoraptors. These are small bipedal predators, and also the plesiosaurs. These were the ancestors of the long-necked dinosaurs. But even during this early Triassic period, dinosaurs still were not dominant. There were actually lots of other reptiles that they were competing with, and so they were playing a minor role. However, at the end of the Triassic, 201 million years ago, they got lucky again. The dinosaurs were saved by the end Triassic extinction event. Huge volcanic activity was occurring in the Atlantic, and this caused lots of CO2, and this warmed the planet, wiping out almost all of the dinosaurs' competition, allowing the dinosaurs to migrate across Pangaea all around the continent. And so the Jurassic period is when these dinosaurs begin to really get massive and really become dominant, okay, with things like the sauropods began, like the Brachiosaurus. The stegosaurs appear with body armor and tail spikes. The Allosaurus, this was a branch of the theropods that became bigger and larger and became apex predators. Also the Cryolophosaurus, this was an Antarctic dinosaur that lived in the colder polar snowy conditions. It was a very large and very feathered theropod. This was the skilled part of the dinosaurs, okay? These feathers really helped them dominate. Also, the fact that they were warm-blooded allowed them to live in all these colder climates. Also, the fact that a lot of these dinosaurs began to herd together and they began to migrate across the continents, and there were dinosaur highways with various species walking together across the world. And so by the end of the Jurassic period, by 150 million years ago, dinosaurs were really dominant across all continents. By the early Cretaceous, dinosaurs were in their golden age with things like the ceratopsians, the triceratops. The triceratops, along with the hadrosaurs, like the duck-billed dinosaurs, they were both plant eaters and they flourished together. Certain types of dinosaurs would stick together even though they were different species, and that's what allowed them to really flourish. This is where we see dinosaurs really begin to diversify. Really strange features emerge out of this period, like the ankylosaurs with these armored tank-like bodies with like tailed clubs. And the raptors, like the velociraptor, they began to hunt together in packs. They became really advanced hunters, and they began to flourish as well. The Cretaceous also saw the rise of the tyrannosaurs, like one of them being the T-Rex. As Pangea began to split, dinosaurs went their own ways and evolved differently. And on their own different continents, they co-evolved and became bigger with one another, like the Titanosaur, for example. It became bigger partly because it was being affected by other dinosaurs around it. The Dinosaur became 100 feet long. They became larger to prevent any predators from touching them. I mean, they were untouchable. They were not just like these weak herbivores. They were strong. They were actually very aggressive as well. We also see a group of dinosaurs thrive in Alaska in the cold polar regions where it was dark for months. They would actually hibernate. There's some evidence of them burrowing underground and hibernating. The late Cretaceous was peak diversity for the dinosaurs, as well as the ecosystems around them. We see flowering plants for the first time, and grasses, and all kinds of exotic trees, until the asteroid impact about 66 million years ago wiped out all the large dinosaurs that were non-avian, but the ones that could fly, they survived and carried on and became today's birds. So in the next couple of videos, we're going to go more in depth about this extinction event, talk about how we know it happened, and what exactly happened, and all the cool stuff in between. Stay tuned. What exactly happened on the day the dinosaurs went extinct? Let's just say it was way more terrifying than you think. The asteroid that struck the Earth that day was 7 miles wide, or about 10 kilometers wide. People don't realize how big that is. That's how high planes fly in the sky. So imagine being right next to this thing and looking up at it, and it's being as high as planes got, taller than Mount Everest. And that rock struck the Earth at 45,000 miles per hour. That's 20 times faster than a fighter jet. The rock struck the Yucatan Peninsula, or modern-day Mexico, but back then there wasn't a coast, it was shallow waters. And so the waters were maybe 300 feet deep, but the rock was about 10 kilometers or 7 miles high, okay? And so that thing struck as if it was striking land. The water vaporized. The rock itself immediately pulverized. There was so much energy in the impact that everything within a 700-mile radius was completely vaporized on impact. Dinosaurs, rocks, trees, they were all pulverized immediately. And the seismic waves that this impact caused, they shook the entire Earth. They eventually made their way across the entire Earth. Every dinosaur on the planet would have felt shaking in any given area of the Earth. This is just the beginning. 15 minutes after the impact, all the liquid molten rock that was liquefied around the impact that went into the air started to rain back down. But it didn't rain back down as molten. It cooled into shards of glass. So for hundreds of kilometers around the impact area, it was raining glass on the dinosaurs. But that wasn't all the stuff that was ejected from the impact. A lot of it went into space. And 30 minutes later, it came back down through the atmosphere. It reheated again. Okay, and all that rock started to reheat in the atmosphere, and it baked the atmosphere, okay, like an oven. So it was just glowing stuff in the atmosphere, and this worked like an oven to reheat the surface. Forests started to spontaneously combust. Wildfires across much of the planet would break out at this time, especially near the impact. But just imagine forests just immediately bursting into flames for thousands of miles around the impact site. Within an hour, shock waves from the impact sent hurricane force winds pushing through, blowing down trees, blowing down forests, blowing away dinosaurs for hundreds of miles from the impact. Heavy clouds full of debris from the impact made their way across the Earth with really strong lightning, which sparked even more wildfires across the planet. 3 hours in, huge tsunami waves generated by the impact make their way across North America, inundating land for dozens of miles inland. Dinosaurs would have seen 1,000 or 2,000 foot tall wave crashing on the shores, Okay, they would have been swept away by the waters. Even in central US, okay, near even Iowa, there are signs of floodwaters making their way through the seaway of North America 66 million years ago and into the upper central United States. The tsunami waves reach all the way to Europe. Back then, the Atlantic was smaller. And that was just the initial tsunami waves, right? There were more to come as the Earth continued shaking. In fact, the earthquakes around the Earth were so strong that some scientists believe it triggered the Deccan traps in India. These are volcanoes that some think were erupting before this time, but really started erupting after the impact. These massive volcanoes would have erupted tons of gases in the atmosphere and also lots of lava for 2 million square kilometers it would have covered in India. Within 24 hours, the entire Earth was covered in clouds of soot, debris, and ash, and this blocked out the sun. The sun was so dim that photosynthesis essentially stopped on Earth. Plants stopped growing. The Earth's temperature dropped 15 to 20 degrees Celsius very quickly. It was the worst case nuclear winter scenario. It stayed that way for years. And sulfur in the clouds eventually rained down as sulfuric acid rain, started raining down across the world. Phytoplankton, which rely on photosynthesis, started dying out, and this collapsed the entire food chain in the oceans. Right, the largest marine reptiles went away first. The largest herbivores on Earth began to die out quickly, and so did the carnivores, who fed on them. And this led to a collapse of the entire food chain. 75% of all species on Earth died out. That was perhaps the most devastating day life on Earth had ever seen. How did some animals survive the dinosaur extinction? There's a secret behind their success. The Earth was still dark for months after the impact. It was cold and many plants died, but some plants put life on pause. Within a year after the impact, nearly all animals above 60 pounds in weight died out because they were so dependent on constant calories. Food rapidly became scarce, and so animals had to scavenge for their food or hibernate. And so that's why we see even some large reptiles survive the impact, like turtles and crocodiles. Sometimes they don't have to eat for months or even years, and they can hibernate. They also were semi-aquatic species, so that water acted as a buffer to protect them from the wild temperature fluctuations. In the oceans, the Cretaceous marine reptiles that live near the surface of the waters, they all died out, but fish became bottom feeders, and the ones who could thrive deeper in the oceans, they survived. Sharks, which could survive deeper in the oceans, also thrived consuming the fish. But what saved the day for life on land were seeds and spores. Many plants would produce seeds and spores which would lie dormant for months or even years and wait for the right time to come back and germinate again. And so on the ground, small mammals which would burrow underground, and even birds at the time, which were ground dwelling as well, they were able to consume those seeds for months and years and maintain their calories. Insects like beetles and cockroaches also made out very well during this time because they were consuming decayed organic matter, decayed fecal matter as well, because they were detritivores. So for the first few years after the impact, these animals were able to survive just getting by with minimal calories, minimal sunlight. But as the dust settled, about a decade after the impact, light peered from the sun onto the surface again. And those seeds that lie dormant for many, many years germinated again. Once again, they revitalized, came back to life, as well as the spores of ferns. Ferns produce spores, millions of microscopic spores, which can quickly come back again with a little bit of moisture and light. So about 1 million years after the impact, ferns began to dominate around the world, as well as insects and beetles. They really dominated. Ecosystems were still sparse here, but we see a fern spike in the fossil record. It took a couple more million years for the ecosystems to restore back to normal. Forests around the world began to grow back again. Flowering plants began to dominate again. And all the scavenging animals, like the small birds and mammals, began filling in their new niches, as all the predators of their past are gone. Within 20 million years, birds begin rapidly diversifying into aquatic niches. Ducks, swans, geese, they become aquatic specialists. In niches in trees, they become perching birds. Conifers were devastated after the impact. that wiped out many of those hard, woody trees with needles and cones and made way for angiosperms, trees that are better suited for birds who they can stay there and perch and live and nest in these trees. They also produced fruits and nectar and seeds which birds can thrive on. Before the impact, these birds were ground dwellers. They lived in the ground or on the ground, and so they were hiding from the dinosaurs, like especially pterosaurs, which dominated the skies at the time, and they would come by the trees and rainforests and consume these birds. And so these birds were previously forced on the grounds, but now they were open up to this new niche and they could rapidly diversify. And so their wings evolved, their beaks evolved to consume different types of foods, their migratory patterns evolved, they started migrating across the planet. As mammals and reptiles co-evolve, predatory birds like owls and eagles and hawks, they begin to dominate the skies, predating on mammals. And so even after the impact, dinosaurs still were dominating for a good 30 million years. Because remember, birds are dinosaurs. But if it weren't for the seeds and spores that helped boost the ecosystems after the impact and helped the birds survive and all the other animals survive in the food chain, there would have been way more animals that would have gone extinct. This just goes to show you how resilient life can be on Earth. I mean, anything, asteroids, volcanoes, it don't matter. Life on Earth always finds a way. Stay tuned for the next video in this dinosaur series. How do we know the dinosaur extinction happened and all the details about it? A lot of you guys are asking me, well, were you there? I wasn't. But the puzzle pieces were. In the late 1970s, geologist Walter Alvarez was working in Gubbio, Italy, looking at foraminifera fossils. These are microorganisms that were in the waters that would deposit these shells, these chalk-like shells. He was just trying to figure out how these forms evolved through time. So he's looking at the geological layers and he found that at a specific boundary, there were lots of these forms, and then past it, there was almost none left. And he noticed right where these forms began to disappear was a gray thin layer. And so he realized, yeah, this means that something bad happened, but what? Walter asked his father, Luis Alvarez, who was a Nobel Prize winning physicist, about the layer, and Luis suggested that they looked at the elements in the layer. They both analyzed this thin gray layer, and they found it had high concentrations of iridium. This was very rare to find in the Earth's crust. The high amount of iridium signified that this thing came from space, whatever it was, not the Earth, because when the Earth formed, iron likes to combine with iridium and it sunk to the core, leaving the crust with less of it. At first, they hypothesized that maybe this iridium came from a nearby supernova explosion, a star that exploded, and all that iridium fell down to the Earth. But as they referred to other scientists about this, the other guys were like, let me take a look at my samples of this layer, because everybody knew about it, but they didn't know about the high concentrations of iridium in it. And so when they realized that all around the world there were very similar concentrations of iridium in this layer, they realized, okay, this is too much to be coming from a supernova explosion. They calculated it given how much they found globally and predicted that this would have came from a 10-kilometer wide asteroid. So in 1980, Walter and his team published their paper about this asteroid that caused the extinction at the KT boundary. But scientists were skeptical. They were not used to this kind of massive impact happening because they thought the dinosaurs died out very gradually and slowly over thousands of years. And one of the most common critiques was, where's the crater? We should see a big crater if this thing was really that massive, about 180 kilometers wide. And so that led them to the next clue. Where was this crater? Now, most of the Earth's surface is covered in water, and so it's kind of hard to find it in the water. You have to look for evidence and clues beyond the water, offshore. But where? They had no idea. Scientists went back to the layer to find some more clues, and they found glass-like spherules, little tiny beads of molten rock in the sedimentary layers of the boundary. That signifies that there was once a molten rock that cooled as it fell back to the Earth and turned into a glass bead. And then they found another clue in the layer. They found shocked quartz. Shocked quartz happens when you have an immense amount of pressure, and shock happened to a quartz crystal, and its lattice structure literally deforms under all this pressure. This is known to have happened near nuclear test facilities. And since they knew that quartz crystals only form in continental plates, not oceanic plates, they knew that this was coming from an impact near land or in shallow waters. Then, a couple years later in Texas, geologists discover strange river deposits where they see fine layers of mud sediment, but then quickly they see a layer of massive boulders. So what could have caused those massive boulders to be quickly mixed in with muddy sediment? Oh yeah, a mega tsunami. That was evidence that a massive tsunami came by and moved all those boulders and rocks into the sediments in Texas. So scientists got their next clue. Yeah, the impact was probably somewhere near Texas. Soon after that, scientists discovered tektites in Haiti. These are little molten rocks that became droplets. Another major clue that the impact was near the Gulf of Mexico somewhere. Years go by, scientists are still trying to figure out where this crater is. But then in the early 1990s, Alan Hildebrand was a geologist giving a presentation on this research. And a journalist in the crowd, Carlos Bayars, heard this. And he realized, wait a minute, I was reporting on something similar to this story in Mexico about a weird crater site. In the late 1970s, a researcher for the Mexican oil company called Pemex was looking to drill oil in Mexico. And they used gravimeters to look at the gravity field in this place in Mexico, near the Yucatan Peninsula. And they discovered that there were these weird indents. There were these weird, looked like an impact crater site. So Carlos told Alan about this, and Alan got core samples of that area, and they found shocked quartz. And they found molten rock droplets in the sample. The team went there, they measured it, and they found it to be exactly the size they predicted it would be given how large the asteroid was. And they found it in the exact area of the KT boundary. That's how the crater was discovered. That's how we know that the asteroid struck shallow waters and it vaporized on impact, and all that soot and debris and iridium from the asteroid went into the atmosphere, and it mixed in with all the other stuff and deposited as this KT boundary layer all around the world, which is what we now see. And that's how we know that molten rock was flung into the atmosphere and came back down radiant glass. In fact, in 2019, researchers in North Dakota found fish gills in the geological layers full of these glass beads, these ancient spherules. They found tons of fish with this glass in their gills. And in 2022, a study was done to confirm that the temperatures globally would have dropped by 15-20 degrees and photosynthesis would have stopped. So the evidence is recorded in the earth around you. And when we look at the Cretaceous-Paleogene boundary, we find very little dinosaur fossils after the boundary, which means that there is a mass extinction. And you put all these puzzle pieces together, that's how we understand what happened. This took many people in many different disciplines of science, paleontology, geology, geochemistry, climatology, all these different sciences had to come together to create this model of what happened 66 million years ago. And that is how science is done. Stay tuned for the next episode in this dinosaur series. If the asteroid that wiped out the dinosaurs approached the Earth just 2 minutes later or 2 minutes earlier, it would have missed the Earth completely. And this raises the question, what if the dinosaurs never went extinct? Like throwing a dart and hitting the bullseye from thousands of miles away, the asteroid struck shallow seas, which was the perfect recipe for disaster for the dinosaurs. If the asteroid was nudged just a teeny bit in either direction, it would have struck the deep ocean, where the impact would have caused earthquakes and tsunamis, but all the ejecta would have been absorbed by the waters, so there'd be no soot in the air, very little ejecta causing any kind of global nuclear winter, which means the dinosaurs would have been saved for the most part. If the asteroid missed completely, we'd be living in a very different world. The evidence suggests that the dinosaurs were thriving up until the late Cretaceous. Even through all those volcanoes and all those things, they were still thriving. So if the impact never happened, they would continue to thrive and be dominant. They'd still be dominating all the other species, including mammals. Our great ancestors were there 66 million years ago. They were just small shrew-like animals. So our ancestors stayed small because that's what helped us survive. In the holes, underground, under the forests, we'd hide from dinosaurs trying to eat us. However, the Earth would have cooled down over time throughout the Cenozoic, as it did. In fact, the Earth would probably cool even more if the impact never happened, because the impact sent out tons of CO2 from the carbonates it impacted into the atmosphere, and it also burned all those forests. Those wildfires also emitted tons of CO2. So during the long term, the Earth probably would have been slightly cooler through time. This means that dinosaurs would have gotten smaller through time. 34 million years ago is when the Antarctic separates from the other continents and the Earth begins to really cool down. We see permanent ice caps at the poles, and we also start seeing grasses expand. So because the impact happened, this allowed the mammals to grow larger through time and take over those grassland niches around the world. And so herbivorous mammals became dominant, as well as carnivorous mammals like lions and tigers. But if the impact never happened, we probably would see dinosaurs like hadrosaurs and ceratopsians, the herbivorous ones. They would take over those grassland niches. Instead of woolly mammoths, we might see woolly triceratopses or woolly hadrosaurs. Grasses was a fairly new type of vegetation during the late Cretaceous, so dinosaurs were just beginning to consume some grasses. But it wasn't widespread like it is today, so dinosaurs would have adapted to eating more grasses and flowering plants. Flowers were also relatively new when the dinosaurs were in the late Cretaceous. But the dinosaurs allowed the proliferation of flowers because when they were stomping on the ground in these forests, uprooting trees and uprooting all this vegetation, dinosaurs were engineering the ecosystems to make them more open spaces where flowers can thrive. But the impact really devastated flowering plants and stalled their progress for millions of years. The extinction of the dinosaurs allowed forests to thrive where our ancestors would live inside the trees, and they would eat the nuts and eat the seeds and eat the fruits. Our ancestors needed the dinosaurs to go away so that we could take over those forest niches, allowing primates to emerge and evolve in their little social groups. Now, would the dinosaurs be intelligent? Well, a lot of people expect that inevitably intelligence emerges and evolves, just given time. Well, that's not true. One of the biggest reasons why we're so intelligent is because of our hands. Our hands allowed us to manipulate our environments and use tools and do all kinds of things with our hands. This served as a feedback loop of intelligence for us. Our hands manipulate the environment, our brains co-evolve to match it, and then we use even more sophisticated tools with our higher brain functioning. And so it was a feedback loop of intelligence. The dinosaurs didn't have that. Dinosaur arms were smaller, so they weren't grasping things with their arms like we were. Plus their hands, although graspable, they were just using them to attack prey. So their hands did not evolve the same dexterity that ours did while we were grasping trees and branches when we were living in trees. Without that evolutionary trait, we would have never been able to develop tools and become intelligent using our tools together and live in societies. And so it's highly unlikely that the dinosaurs would have ever evolved intelligence like we humans did. However, the carnivorous dinosaurs would have adapted with the herbivorous grazing dinosaurs, just like today's lions and cheetahs adapted with the gazelles. The carnivorous ones likely would have hunted in packs, as that we know today in lions increases their success rate in hunting. And so pack hunting may have allowed the dinosaurs to evolve a kind of language when they were hunting. Dinosaurs didn't have larynxes like we do. They had something more like bird-like syrinxes, where their words might be pronounced with whistles and clicks, things like that. So you can imagine if you transported yourself to a different timeline where the dinosaurs are still alive, you might hear complex bird calls, maybe complex dinosaur language around the world. Now, dinosaurs didn't have a neocortex, just like modern day birds do not have a neocortex. This is a mammalian feature of the brain that helps us process emotions and memories, and we combine those two together. This enables very complex social hierarchies and social understandings. The dinosaurs wouldn't have had that, so they probably would not have developed societies such as ours. So think of how lucky we are. Think of the butterfly effect that has happened throughout these past 66 million years that enabled us to be here, to be on TikTok, to be human with all the richness and complexity that comes with us. This is a rare experience. You can't take it for granted. Looking back in the past reminds us that we're all beholden to Mother Nature and chance. That chance alone brought us the remarkable lives and deaths of the dinosaurs.